We are going to look at page 13 of homework packet 17, and it's this idea of free energy or Gibbs free energy, which is really the combination of two factors. The enthalpy and the entropy combined to make up the what we'll call free energy of a system. So let's do a little bit with entropy. And entropy is the degree of disorder, okay, or number of probable states. And it is favorable. The natural progression toward things is a change in S or an increase in entropy, or delta S is greater than zero. So what are some things that we see delta S is increasing, going from a solid to a liquid, or a solid to a gas, or a liquid to a gas? Okay, there are more probable states. And you can kind of think of a gas, especially, would be the molecules are most random. If you're looking at an equation, count moles of gas. We did this when we looked at equilibrium, and we're looking at pressure systems. Because the gases have the highest entropy, count the moles of gas. The side of the equation with the most moles of gas would have the most entropy there. There are some more particular ones right here. I'm going to go down and highlight this one. A separate solute and solvent will have less entropy than when you mix them and combine them together. So when you mix things, it's going to increase the entropy. However, be careful here. When a gas escapes a solution, it actually is escaping and going into more probable states. So that would be an increase in entropy as well. So you don't open up a can of pop and it starts fizzing. That would be an increase in entropy. Okay, so reactions essentially have two driving forces. And to proceed toward the products, there are two things. We look at the enthalpy, which is the heat energy, and we talked about how things want to go from a higher to a low heat content, where exothermic reactions are the ones that are thermodynamically favorable toward the products, if that were the only factor we were considering. But there is also this factor of entropy. Things also tend to become more disordered or more random. So we get this delta H negative, which is exothermic, and delta S positive, which would be an increase in entropy. Gibbs free energy really puts those factors together, and we have an equation. I'm on a video, Isaac. Thanks. Delta G equals delta H minus T delta S. So notice if it's favorable for delta H to be negative, then it's favorable for delta G to be negative. Also, if delta S is positive and it's favorable, minus S, a minus a positive would make this negative. So both of these conditions would make delta G negative. So therefore, we say when delta G is negative or less than zero, the products are favored in equilibrium, and this corresponds to a K is greater than one. The opposite, when delta G is less than zero, then delta G is positive, and that would correspond to a K as being less than one. And when you are in equilibrium, K does not equal zero. That looks like a mistake. It should be K equals one. And that would be, if delta G is zero, then K would be equal to one, and that would be an equilibrium right there. Okay, what is this T here? This is temperature, and we'll see how that comes into effect in the next little segment. Okay, so let's go here, and we have a little diagram with some examples. So I'm just going to look at an example when delta H is positive, delta S is positive, and then what will delta G be? Well, it will actually depend. And if I think about this, delta H being positive, that is not thermodynamically favorable for the products. But delta S is thermodynamically favorable for the products. So it depends on what the temperature is. And I could look at this and say, oh, temperature is the one that really the entropy depends on. So if I look at this and say, oh, entropy is positive, if there's a high enough temperature, then this delta S term will dominate the delta H term, and this delta G will become negative right here. And here is an example of that. If I talk about a phase change of H2O liquid going to H2O gas, we know sometimes we get it as a liquid, sometimes we get it as a gas. We know at higher temperatures, it turns to a gas, because if we raise the temperature, it drives equilibrium, or just from our experiences. How does this look in terms of what we're talking about here? Notice it's exo or endothermic, so delta H is positive. That's not thermodynamically favorable. It wouldn't go by itself if it weren't for the entropy. But going from a liquid to a gas is thermodynamically favorable toward the products because it's becoming what? More probable states, more random right there. So it depends. If you get to a high enough temperature, okay, and that really what we think about like that as a boiling point, then it's going to go from a liquid to a gas. All right. What about the opposite case when delta H is negative, which would favor forming products, and delta S is negative, which would not form products? We're going to see the opposite thing. Okay, at lower temperatures, the delta H by itself would be negative and make delta G negative, which is thermodynamically favorable toward the product. But that delta S being negative is going to fight against that. At a low enough temperature, this won't matter as much. So I'm just going to take the opposite example, H2O gas to H2O liquid giving off energy, and I can say, okay, um, I know that delta H is negative, okay, which is thermodynamically favorable because it's exothermic, but it's also becoming less disordered going from a gas to a liquid, which is not thermodynamically favorable. So which one wins out? Well, it depends on the temperature. The lower the temperature, the more likely you are to be a liquid. The higher the temperature, it's going to be more favorable to be a gas. So it depends on that situation. Okay, let's go to another example. And this is, what about delta H is negative? That's thermodynamically favorable, it's exothermic, and delta S is positive. We have an increase in entropy. So that would be like hydrogen peroxide breaking into water and oxygen. Notice it's exothermic, which is thermodynamically favorable. And notice 0 moles of gas on the left, 1 mole of gas on the right. That's thermodynamically favorable. So this will be thermodynamically favorable at all temperatures. And again, this is something that's thermodynamically favorable. Kinetically, it can be a really, really slow reaction, though, unless you have a catalyst, which is so let's look at another example, and we're going to say, let's look at the opposite of this. What about adding energy to H2O and oxygen and forming H2O? I'm kind of hoping this isn't going to happen because when I go grab my glass of water out of my water bottle, I hope I'm not drinking hydrogen peroxide. And this is not thermodynamically favorable. And let's just take a look at why. Well, again, it's exothermic or endothermic. So that is delta H is positive. That's not thermodynamically favorable to the products. And delta S is negative, meaning the entropy decreases, which is also not thermodynamically favorable, no matter what the temperature is. So it's not thermodynamically favorable for your water to combine with oxygen in the air to form hydrogen peroxide. So even though there's no reaction, that can be a good thing because we don't really want that reaction before we drink our water. So hopefully that kind of helps you just get an idea of how we're looking at delta H, delta S, and then looking at the overall effect and delta G, and that's kind of the combined factor or the free energy, taking in consideration not just the enthalpy like we did before, but also that entropy factor. Thanks for watching.